Hi everyone. In this Connect with Networking video, we're going to continue our discussion of Chapter 5, the transport and networking layer of the network stack. Let's go ahead and get started. One of the principal responsibilities of the network layer is routing, and this is how we identify what path we're going to have a packet take to get from its origination to its destination, or its sender to its receiver. And the way this is accomplished is by using routers, which are network devices that direct traffic from one location to another, and routers take advantage of routing tables, which they use to make their routing decisions. These routing tables show which path to send a packet to get to a specific destination from a specific location. So for example, if a packet arrived at router A, and its eventual destination was location G, what paths could it potentially take? Well, router A would have already looked at all of the possible ways that a packet could flow from one location to another. So it would consider paths like A, B, C, G, or A, B, E, F, C, G, or A, D, E, F, C, G, or A, D, E, B, C, G. And it would consider a variety of different factors depending upon the protocol it's using to determine the best possible path. The only thing a router is going to do is direct a packet to the next location. So the router is not providing a set of directions from its very first location to its very last location. It's only directing a packet that has arrived at a particular routing location to the next routing location. So router A really only has two answers to the question, which direction should I go? It will direct traffic towards destination B or towards destination D. Once a packet arrives at that next destination, that next device would be responsible for choosing the next direction that a packet has to flow. So if you did flow to B, B would be responsible for sending something towards either C or E, depending upon where that eventual final destination is. Once you arrived at router C, it would be responsible for sending things towards F or G, depending upon, again, what your final destination would be. Let's take a look at an actual network. In this case, we have a variety of different routers that are supporting local area networks, but that are also connected to each other on some backbone networks. And you can see the various subnets represented by the first three digits of an IP address. So 10.10.51.x represents the subnet for a local area network connected to the router in the upper left-hand corner. Some of these routing devices would have very, very simple routing tables. If I am a router that is supporting traffic from the 10.10.70 subnet, or a local area network that's connected to the rest of my network, using this router, there are only two possible choices. If traffic hits this router and it is intended for another device on the same subnet, 10.10.70, the traffic is directed back into that local area network. If this router receives traffic for any other IP address, its only choice is to send it up to the next router. It doesn't designate the specific overall path for the packet that is leaving its local area network. It just sends it up to the next network device and allows that device to determine where that particular packet should go next. So if the packet was actually meant for 10.10.51, the router that it first encounters at the 10.10.70 junction would send it towards path 2. It would hit the router at the 10.10.52 junction, and that router would look at its own routing table and decide on either path 1, 2, 3, or 4, and would send that packet along path 4. When it hits the router at the 10.10.51 junction, that router would look at its own routing table and determine that the particular packet needs to come into its local area network, so it would send it along path 1. The router at 10.10.51 has a lot more options available to it. Traffic that is designated for its own local area network would flow along path 1. Traffic that is meant for 10.10.52 would flow along path 2. For 10.10.34, it would flow along path 3. And for anything that it didn't recognize, it would flow along path 4, something outside our particular network. But there are additional choices that it has to be aware of. If something is designated for 10.10.53, it would have to decide how to get traffic to something that is more than one node away. And in this case, the appropriate choice would be to send along path 2 and then allow the router at the 10.10.52 juncture to direct the next step. For traffic for 10.10.70, similarly, we'd send it along path 2 so that the router at 10.10.52 could send it along the appropriate next path. Sometimes routing decisions are made by a centralized computer, but this is a fairly rare model for today. The more common model for routing is decentralized routing, where each of the nodes makes decisions independently of one another. Sometimes information is exchanged from the various network devices to prepare the routing tables, but the devices themselves are independent. And this is the model that is used by the internet. Another consideration for routing is whether our routing tables will be static or dynamic. Static would be something that we set up once and then rarely change. Dynamic would be routing tables that are periodically updated, looking at the various speeds that we're seeing on the network and the various node availability. So if a particular router is malfunctioning and that path is currently not available to us, we could dynamically route around it and use an alternative path if necessary. Router tables would exchange information using protocols to update their particular tables. There are a couple different routing algorithms we use for dynamic routing. One is called distance vector, which is a bit of a misnomer because instead of considering actual distance, it counts the number of hops between two devices and chooses the path that has the least number of hops. This is a naive approach to determining how long it would take for a packet to get from one place to another, but it ends up being fairly accurate. If you do want to be more specific, you could use a link state, and this would consider both the number of hops and the circuit speed and particular traffic congestion. This provides a more reliable, up-to-date path from origination to destination, but of course the router has to be more intelligent about its process, so the router is probably more expensive. One particular routing protocol that's been used for dynamic routing is Routing Information Protocol, or RIP. This is used for interior routing, and it's typically used by network managers that build the routing table that are then broadcast periodically to every other device. This does mean that when new computers are added to the network, the router has to count the number of hops, determine the shortest route to that specific device, and then add an appropriate path to its routing table. This works very well in small, less complex networks. For a more complicated network, we might consider something like Open Shortest Path First, or OSPF. This is also a dynamic routing protocol that uses link state, so it considers not just the number of hops, but the speed of the network and current congestion to give the most reliable paths. This is less burdensome on the network because the updates that are sent from one device to another are only sent when updates occur, not on a schedule like once a minute. So we don't update the other routers unless we've made some sort of change. Another dynamic link state protocol that was developed by Cisco is called Enhanced Interior Gateway Routing Protocol. And this uses yet more statistics to determine the best possible path between 2 points. This is more complicated than some of the other protocols we've discussed, and routers have to take into account their own routing tables and the routing tables of their neighbors to make the best possible decision. These devices are very sophisticated, but they do provide the best possible routing path. While individual networks might pursue a variety of different internal protocols, when we want those different networks to communicate with each other, we need some sort of common protocol for those larger distances. And the protocol that's been adopted by the internet for exterior routing is called Border Gateway Protocol. It is a dynamic distance vector protocol, far more complex than interior routing protocols, and because of the very large number of paths that traffic can take, the number of actual routing paths considered by BGP is limited. So think about making a plan for a cross-country trip where the only thing you really consider are interstate highways to eliminate all the other possible pathways you could take from one location to another. This picture shows how a variety of different local area networks could use different interior routing protocols, but they connect to each other using the border gateway protocol. When traffic is flowing through autonomous systems, the originating message doesn't have any control over what their protocols might be, and it really doesn't matter. As long as the traffic flows from network to network to network and reaches its final destination, any protocol could be used in the autonomous systems, and the BGP protocol will be used between those systems. Let's look at a couple of TCP/IP examples to get a better illustration of how traffic might flow from one device to another. We're going to assume that we know our device's own IP address. The device also knows its own subnet mask. It knows the IP address of the default gateway, which we'll consider a router. And it knows the IP address of at least one DNS server in case it needs to make a translation from a URL to an IP address. All of this information would likely be originally obtained from a configuration file or from DHCP. This is the example we'll be discussing. You can see there are multiple devices that are on the same overall network. Each network inside a building has a router that connects its local area network to a backbone network. You can see that the routers have multiple IP addresses because routers face both inside their local area network and outside to the backbone network. And similarly, each router has two hardware addresses, the one that's inward facing and outward facing. Each building has a subnet, and in this case, our subnet is going to have 3 decimal numbers, and the 4th decimal number will be dedicated to individual devices within that building. You can see that individual clients or servers inside buildings have IP addresses assigned to them that fit their particular subnet and have Ethernet addresses that are assigned to their hardware. In this case, we're going to look at how our client in building A might communicate with other devices in this network. Let's look at the first example, where a client is going to request a web page from a server in its own building and knows its own server's IP address. The client in building A would create an HTTP request at the application layer and send it down to the transport layer, where that message would potentially be segmented and add some additional header information, including the source and destination ports. It would send those segments down to the IP layer or network layer, where the appropriate IP address for the local server, 128.192.98.53, would be associated with that particular packet. It would then add an Ethernet frame with its local gateway's address. We're looking at 00, 0C, 00, 33, 3A, 0B. Our client would then send this Ethernet frame using the physical layer up to the local router. The router would receive this frame, which would be addressed to it at the data link layer. It would remove the Ethernet frame, examine the IP address, compare it to its routing table, and determine that this is a packet that is meant to be received by one of its local devices. It would add the appropriate Ethernet frame to the local web server, and then send that Ethernet frame to that web server inside the same building. That web server would receive the Ethernet frame and remove the header information. It would remove the IP header information. It would desegment the message at the transport layer and then send the appropriate information based upon the destination port to the application layer on the web server. Let's consider a second possibility, where our client in building A is requesting a web page from a server on a different subnet. The client does know the server's IP address, though. In this case, the client would create an HTTP packet, send it down to the transport layer, where again it would be segmented and sent down to the network layer. We would add the IP address for the web server over in building B. Once we do so, we would send down to the data link layer, and the hardware address would actually be for our local router or our local gateway. And then we would use the physical layer to broadcast a signal to our local router. The local router would receive that packet, which would be addressed to it based upon its hardware address. It would then remove the Ethernet frame, examine the IP address, compare it to its routing table, and determine that the specific packet is meant for someplace other than its local area network. This router only has two possible paths: back into its local area network or up into the backbone network to a specific router that's located on the backbone network. So the router would choose to send this packet to the next router on the network, specifically the router that has the address 128.192.254.5 and their Ethernet frame 000C00333AF. It would then craft that Ethernet frame, send that frame across the backbone network, where it would be received by the router in building B. That router would remove the Ethernet frame for itself, examine the IP address, determine that that IP address belongs to its local area network, attach the appropriate Ethernet frame for the web server in its own building, and then send that Ethernet frame to that web server. That web server would receive the Ethernet frame, remove the frame, remove the IP addressing, remove the transport layer, headers, and finally deliver the appropriate content to the appropriate application layer. Let's look at one more example where our client is requesting a web page from a server in our own building, but at this point the client doesn't already know the server's IP address. Before the HTTP request can be sent, the client would have to make a DNS request to determine how www.1.anyorg.com resolves itself in terms of an IP address. So it would craft a DNS request using UDP. It would address the Ethernet frame to the local router. The local router would receive that Ethernet frame, examine the IP address, which would be for the DNS server, attach the appropriate Ethernet frame for the DNS server on the backbone network, send that packet to the DNS server. The DNS server would receive that Ethernet frame, remove it, examine the internal contents and determine that it's a DNS request, look up the appropriate information in terms of what URL matches what specific IP address, and then send a DNS response back to the client using a reverse process to what we just described. When the client in building A receives that DNS response, it would then know the appropriate IP address for the web server, and then we would repeat our example from step 1, where we'd be addressing a message to a server in our own building. Let's consider what happens when information moves from place to place on our network. Clients and servers will have packets that move through all the layers. The origination of the message will move from the application layer all the way down to the physical layer, and then the destination will have information move from the physical layer all the way back up to the application layer. For gateways and routers, packets are going to move from the physical layer to the data link layer, and then move up to the network layer, where the router will use IP addresses and routing tables to determine how next to move this message. So at each stop along the way, other than the final destination, Ethernet frames are being removed, IP addresses are being used to look things up, and then a new Ethernet frame is being created to deliver the message to the next node. Everything at the network layer and above is never changed, so you don't see any of the original content being modified in any way while we're moving messages across our network. And here's a picture of how we moved a packet from building A to building B. So you can see the message move from the application layer all the way through to the physical layer in building A from the client. It was received by the local gateway router. That router removed the Ethernet frame, examined the IP address, and created a new Ethernet frame for the gateway router in building B. It sent that packet to the gateway router in building B, which removed its own Ethernet frame, examined the IP address, and created a new Ethernet frame for the final destination. It then sent that packet to the server in building B, which removed the Ethernet frame, the IP address, the TCP header, and then finally delivered the contents to the web server. The biggest implication for management in this chapter is that the only real standards worth considering are TCP and IP. This is what's used on the internet. It's widely used in most local area networks. It's also used in backbone networks, metropolitan area networks, and wide area networks. Everybody is standardizing on TCP IP. It's also worth noting that there has been a slow transition to IPv6, but we anticipate that this will continue to increase as we continue to exhaust IP addresses out in public, so expect more widespread use of IPv6 in the future. That's it for this video. Thanks so much for watching. See you next time.